Hello, I'm Júlia Borràs, and I'm going to be introducing the work knowledge representation to enable high-level planning in cloth manipulation tasks. When it comes about manipulation tasks in general, we have this execution loop where we have the decision-making module that selects what is the action that needs to be executed, then the execution module that actually performs the action, and then we need to recognize in what state we landed so that we can again decide what is the next action that we need to do. The challenge in cloth manipulation comes at the state recognition. That is why most of the state-of-the-art actually tries to solve this state recognition problem, which normally is focused on ungrasped cloth state. That means identifying if a cloth is folded, how it's folded, or if it's flat, if it's crumpled, where the corners are. And what we propose is to add the grasping state and the environmental contact state in this definition of the scene, because this is going to simplify a lot the states, and also is relevant in order to segment the motions and the tasks into more meaningful building blocks to then understand what is the steps in action that we are doing. So our idea is to have this graph representation so that each one of the nodes in the graph is a state of the scene that simplifies the state recognition, but then also has this low level, can store each one of these states, these low level features that allows to execute the action. For instance, the location of the corner that we need to grasp in order to fold in a certain way. And also this graph representation can be directly thought as a PPDL planner, as we will see in this work. And in addition, we want to be able to learn these graphs from human demonstrations. So this is an example of this graph of transition between scene states. This corresponds to the example that I will be working today with, which is folding a napkin in 3 folds. And each one of these states correspond to a scene, a frame of the scene that corresponds to a change in the grasp, the relationship between the environmental contacts, the object, the deformation of the object, etc. So we are going to actually now go in deep on how we define each one of these states. We have information about the grasp type, the grasp location, and the cloth configuration states. I'm not going to go too much in detail into the grasp type. We have this paper from 2020 where we demonstrated that most of the cloth manipulation bibliography only uses the pinch. But of course, there is a lot more when it comes to grasping. And if we use the correct grasp type, we can really simplify the dynamics of the manipulation. And we define this framework to define grasp type for clothes that the object doesn't have any shape, with geometries like points, lines, and planes that can be either part of the robot or the environment. And then we can combine the geometries to create these opposing forces that define a grasp. And for instance, that would be the usual, the pinch grasp, but combining different geometries, we can obtain a lot of variety, and this allows us to define double like bimanual grasp also, and both humans or robotic grasp. And here we see a couple of examples. For instance, when we have this contact with the table external, we can add, this is actually a combination of 3 grasps, the 2 pp plus the gravity with the table. This is a non-prehensile graph. So also the graph location is very relevant. What we do is define a local coordinates on the object, which in this case is a square, but it could be done for any shape. And these are labels, but can be done with coordinates, and they are with respect to the subject that is manipulating when it's on the table or when it's when it's hanging. So that would be the left corner and the right corner, which are these 2 closer to the subject, or the 2 that are hanging at the top. And this would be the far left, the far right, etc. And this is relevant because if we want to encode what a task is doing only with grasp type, then this is probably not enough. This is a relevant task, which would be the pinch and slide or the tracing of an edge that we as humans do a lot. If we define this only with transitions between grasp types, we don't really understand what is going on. But if we add the location of where it is grasping, we understand much better that it starts grasping the corner, then the second grasp is very close to the first one, and then you slide until you reach the other corner. And finally, we also add these cloth configuration states. The formability, as I already said, this is an infinite state of the formability for clothes. But what we do is really hugely simplifying this in only 5 categories, which is the folded, flat, crumpled, and then partially folded, so not fully folded or not finished to be folded, or semi-flat, partially flat. And of course, now this is a work in progress, so depending on the task, we probably need to add more of these states of the formation. And that's basically the summary. What we have this semantic representation of each one of the states that then we translate it to a graphical representation so that the graphs look nicer, but basically it's the same. This is the graph type. Then if there is table or no, we plot the table. We have a representation for crumble or flat, and this square represents the graphical representation of where is grasping, where the grippers or the hands are grasping. What we can see already for the data that we label at this point still manually is that the variability, when you fix the grasp type, where is grasp, and if it's folded, crumpled, or flat, it's already quite low. So all the frames, they look quite similar. And yeah, I don't really have time to show you all the frames, but this is the idea. And in addition, then we have these transitions, like the edges of the graph would be from an origin state to a destination state, and then we put a semantic label that represents what is the task that is being done. So in the video, we can see how we collected this labeling that at this point is done manually, but I'm going to present also a work where we can autonomously identify some of these states. And here we see that we actually use a software so that we can put a new label every time there is a change in the grass type, the contact with environment, or the deformation. And we do that for several different subjects. And even though all the subjects are instructed to do the same types, that is folding the napkin on the table with 3 folds, they actually do it in a very different way with different number of steps, different number of grasps, etc. Because that's actually the complexity about about cloth manipulation that can be done in many different ways. And our representation allows to capture all these different strategies. And this is for another task, which is also very simple. But again, all the subjects do it in a different way, which is like unfolding and then placing it on the tablecloth. So this is the example of the graph that we obtain. And from the initial start that is crumpled on the table to the final step that is folded on the table. And we actually have to do, we are doing a lot of simplifications of the data here. For instance, we remove, for the initial labeling, we have the identification of right corner, left corner, if we are grasping with the right hand or with the left hand. This is a symmetry that if we want to execute that with robots, we don't really care because the robot is either going to do it with the left or with the right. So we do the task of identifying and removing these symmetries. But also we enforce that at least its transitions appears 3 times because we have a lot of sparsity. There are subjects and sometimes they execute the task, but in a very single tone, like there is only 1 instance. But for instance, that could be the aspect of how it looks the graph when we don't impose these 3, which is also not that bad because then we have an automatic way of encoding that as a PDDM planner. This would be corresponding for the task of folding, putting the tablecloth, which is relevant that you basically pass through from the folded until it's flat hanging here, and then you put it flat on the table. Then the idea is that once we have this graph, we can store it in a comma-separated value format, and then we have a very simple code that translates it into strips language, which where each one of the states defines the initial and the goal positions, and the fluids basically are of this domain, all the possible states that we have, and the transitions are the actions, where the origin and destinations are the preconditions and the effect. This is quite direct. So for instance, in this example, we have 6 different grass types, 7 different grass locations, 4 different cloth manipulations, and a total of 27 transitions. Here is worth noting that we need to, we have semantic labels that are the same, because actually the action of, independently of where you're coming from, we might label it in the same way. For instance, place flat on the table or fold. But they are different actions because they are coming from different states. So then here what we do is label as like fold A, fold B, fold C, etc., etc. And then, like, just to prove that this is possible, we have this subtask, which is from this initial state to this final state. And we use a solver to see if we can find all the possible solutions. What we do is to manually tweak the cost of each one of the edges so that the solver automatically can find all these different solutions. And finally, I also want to show this work that we submitted to IDOS, where we automatically, using deep learning, we can identify 10 of these states in an autonomous way. So the idea is that either learning from humans here, but also like when a robot is doing is if we want to monitor doing an execution of this task to monitor where we are located in this graph, we can identify these states. So basically that's it. As a conclusion, we have presented this high-level representation of cloud manipulations, which is quite a novel field. The cloud manipulation is a very complex task, and there is still not a lot of people working on the high level of how to reason about this deformability. And our representations allows to learn from human demonstrations, which is what we wanted. But maybe if we want to reason about the deformability, maybe we require more extra states. So now we are working on how to find this semantic representation of the deformability itself of the cloth. And also that the grasping information influences a lot on the deformability state. If it's flat on the table, it's not the same that it's flat already grasped. Or even if it's already grasped correctly, but is crumpled, you know that you can reach the flat state in a very easy way. Our representation aims to bridge the gap between the low level and the high levels. That's why we're working on executing these state transitions, doing these motion primitives, but also identifying more semantic states and identifying these relevant features to execute the task, which there is already a lot of literature that does this. So that's it. Thank you. And I'm happy to answer any questions or suggestions that you might give me. Thank you.